Right, so picking back up on the alternating series test, if you're looking at your notes, I'm doing A. So we have the sum as n goes from 1 to infinity of -1 to the n plus 1, n over 2n plus minus 1. I think we did this one in class, but I'll go through it a little slower. First of all, you should see if it's alternating, if the nth term is going to 0 when you take the limit, and if the terms are descending. As soon as it fails any of those three, you can't use the alternating series test. You would have to use another test. But by the fact that the nth term does not equal 0, when we mean the nth term as the absolute value of any term, or really the absolute value of your last term, this goes to 1/2, so it doesn't even go to 0, so it diverges by the nth term test. B. So we have the sum as n goes from 1 to infinity of -1 to the n over ln of 2n. If I check for the nth term of the limit of n over the natural logarithm of 2n as n goes to infinity, I get one of the 7 indeterminate forms, infinity over infinity. So I'm going to do L'Hopital's rule to check the nth term to see if I should even look at it. So the limit, the derivative of n is 1, and the derivative of this is 1 over 2n times 2. So I get the limit as n goes to infinity of 1 over n, or n, so this one goes off to infinity. So it also diverges by the nth term test. So far I haven't even gotten to use the alternating series test. On C, I have, and this one's super important, I have cosine n pi over n. And if you don't understand a series, or even if you do, it's always a good idea to write out a few terms. So I'm just going to see what's happening here when I fill in 1, because this looks really weird. I get cosine of pi over 1, then I get cosine of 2 pi over 2, cosine of 3 pi over 3, cosine of 4 pi over 4 is my pattern. So cosine of pi is -1 over 1, cosine of 2 pi is +1 over 2, this is -1 over 3, and this is +1 over 4. If you notice, this would be the alternating harmonic series. Not the harmonic series, but the alternating harmonic series. So this is super, 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 super important to know about the alternating harmonic series. First of all, it's alternating, so it passes that part of the alternating series test. Second, if I take the limit of cosine n pi over n as n goes to infinity, it will go to 0, because cosine of whatever pi can only be as high as 1 or as low as -1. Meanwhile, you can see this is growing bigger and bigger and bigger as you go. And so it'll be something over infinity, a number over infinity, which would give me 0, so it passes that. And then the third thing you have to have for the alternating series to converge is the terms have to be decreasing as you go. And I know that may sound weird, but they have to be smaller than the one before it, and that does not always happen on certain series. But this one is decreasing as it goes. And so the alternating harmonic series converges. So big deal. The harmonic series, due to the p-test, diverges, alternating harmonic diverges, harmonic series diverges, but the alternating harmonic series, if you had some time, you could even add it up on your calculator, 1 minus 1/2 plus 1/3 minus 1/4 to like 100 or 1,000 terms, and it converges. Alternating harmonic series converges. Okay, so that's the alternating series test. First of all, you'll say that it's alternating. Check that. Then check the limit of the nth term and see if it's going to 0. And then make sure that the terms are decreasing as you progress through the sequence or the series. All right, now going on your worksheets, there's something that's absolutely convergent and conditionally convergent. Absolutely convergent means that it's convergent whether it's alternating or not. Conditionally convergent means under certain conditions a series might converge. Like for instance, here's a, well, we'll do one, A. So I have the sum of -1 to the n power over the square root of n as n goes from 1 to infinity. All right, if I write it out, I'll get -1 over the square root of 1. Then I'll get +1 over the square root of 2, minus 1 over the square root of 3, plus 1 over the square root of 4, which I know is 2. All right, so it's alternating. If you take the limit of 1 over root n, just the absolute value of it, the nth term's going to 0, and the terms are decreasing one after another. And so this series converges. But the question is, if you're asked it, does it converge absolutely or conditionally? Which one does it do? Sorry, that says conditionally. So it converges, and this one converges conditionally. Okay? It's a conditional convergence because if it wasn't alternating, it would have diverged. The sum of 1 over the square root of n diverges by the p-series test. And so if you're ever asked it, which you may not be, but this one conditionally converges because the only reason it converges is because it's an alternating series whose terms go into 0 and the terms decrease. So that's conditionally convergent. In fact, the harmonic series is conditionally convergent. Because the series 1 over n diverges, whereas if it's alternating, then it's going to converge. Alternating harmonic series converges conditionally, which most years is not even on the AP exam. One that would be absolutely convergent is next. We have n is going from 1 to infinity of -1 to the n plus 1 over 3 to the n. They're using n plus 1 to make it start with a positive, so I get 1 over 3 to the first. Then I get -1 over 3 to the second, plus 1 over 3 to the third, -1 over 3 to the fourth, and so on. This is alternating. The limit of 1 over 3 to the n as n goes to infinity is 0, and the terms are decreasing. So I can validly use the alternating series test to say that this is convergent. But is it conditionally convergent or absolutely convergent? What if it wasn't alternating? What would happen if it was just 1 over 3 to the n? Notice this 3 to the n tells me there's something geometric going on here. 1 over 3, 1 over 9, 1 over 27. Even if it wasn't alternating, it would have converged. It doesn't have to alternate because it's a geometric series test where the ratio is less than 1, which also proves convergence. So this one is absolutely convergent because it doesn't have to alternate. There's no set conditions on it. It could alternate if it's, it can converge if it's alternating or not. Whereas the harmonic series is one that's conditionally convergent. All right, the ratio test goes like this. The next test in the next sheet. The ratio test, and by the way, there's, oh no, that's okay. I was going to say there's a word on here that needs to be corrected, but there's not on this page. All right, so if you have a series of non-zero terms, what we can do is we can do sort of like geometric. You know, if I have a series like 3, 9, 27, 81 is geometric, and to find the common ratio, I divide 81 over 27 or 27 over 9. And if that ratio is less than or equal, if that ratio is less than 1, it diverges. This one, I'm sorry, it converges. This one's obviously is going to diverge. But just talking about how you find a ratio, on the geometric test, you say a sub n plus 1 over a sub n, and you want the ratio to be less than 1, the absolute value of the ratio to be less than 1. And so what's interesting is even if it's not geometric, we can still use the ratio test to tell us if it converges. Usually use this test if you have factorials. It's really good for factorials and exponents. And so you see it used a lot with factorial and exponent. Exercise 1 is the sum of 2 to the n over n factorial as n goes from 1 to infinity. The ratio test is take any term divided by the term before it. So to write that, I would say a sub n plus 1 over n plus 1 factorial. That's the term after this one. Divide it by the term before it, which is 2 to the n over n factorial. And is the absolute value of this. And you take the limit of it as n approaches infinity. You see the conditions in the box there. So taking it over here, I have the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial times the reciprocal, which is n factorial, over 2 to the n. So I have the limit as n approaches infinity, and this is n factorial. 2 to the n plus 1 over 2 to the n, you subtract your exponents and you just get 2 on the top, like 2 to the third over 2 to the second. And n factorial is n times n minus 1 times n minus 2, and so on. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2. And so all of these cancel. So you end up with this limit, which goes to 0. They tell you if your ratio is less than 1, that it converges. And so since 0 is less than 1, the series converges. Next example is the sum of n squared 3 to the n plus 1 over 2 to the n. This one's probably too, it's a lot going on, so it's too difficult to do with most of our other tests. And the ratio test is so easy. So I'm going to take the limit as n approaches infinity of n plus 1 squared 3 to the n plus 1 plus 1 over 2 to the n plus 1 over the term before it, which is n squared 3 to the n plus 1 over 2 to the n. Multiply by the reciprocal. This is called the ratio test. And you have n plus 1 squared times 3 to the n plus 2 over plus 2 over 2 to the n plus 2 to the n plus 1 times the reciprocal 2 to the n over n squared 3 to the n plus 1. You can reduce this and it leaves you a 2 to the n on the 2 to the first on the bottom. So you subtract your exponents here, it leaves you a 3 on the top. And you can't cancel these like you could like factorial. Those are two different things, but you can see my highest powers are going to end up being n squares. So those are just going to go to 1. And so the limit is 3/2, which is greater than 1, and so this series diverges by the ratio test. You might want to try example 3 on your own. That ends up going off to infinity, which is definitely greater than 1, and so example 3 diverges. The next page is the root test, which is not on the AP exam, but you know that I will go over it with you anyway, so I'll address it in another video, but for now you won't have homework on the root test. One thing I want you to do right now, though, is go to the last page of today's notes, and under root test you have a box, and it has a 1, 2, 3. The last line should say the root test, not the ratio test, so make that correction. But you're not responsible for the root test.